All right, so let's take a look at page 2 of our week 1 concept check. And here we want to talk about atoms and, as far as chemists go, the subatomic particles that make them up. So again, there's lots of subatomic particles. But for chemists, we take inventory of 3 types. We have the protons, the electrons, and the neutrons. And there's a couple of different pieces of information that we want to keep track of. One is the mass, and so a proton is 1 AMU, and again, AMU means atomic mass unit, and it's basically a way of taking these very, very small things and creating, scaling them to something that's easy to talk about on the atomic level. And so we're going to keep it simple. We're also going to call a neutron 1 AMU. And then an electron, we're going to say, has negligible mass. Essentially no mass. And this is going to come in handy because it turns out that if you have an iron atom or an iron ion that has different number of electrons, they still have the same mass because, again, taking away or adding electrons doesn't really affect the mass to a significant amount because they are so small in comparison to either a proton or an electron. You may remember from the lecture slides that it's like a grain of rice compared to a baseball, just much, much smaller. Now, where these 3 particles are also differentiated is in charge. So we have protons have a +1 charge, electrons have a -1 charge, and then neutrons are without a charge. They're what we would call neutral. And then in terms of an atom, right, the protons and the neutrons are in what we call the nucleus. And then surrounding the nucleus, we have what's called the electron cloud. Right, so that's outside the nucleus. Now, why do we get that particular structure for an atom? And that structure of an atom is very important, and it'll come into play lots of times as we start to understand elements and compounds here in our first couple of units, as we lay the foundation for understanding chemistry, which, as we said, is all about these particles. It comes down to the 4 fundamental forces in the universe. So there's a force that you're all familiar with called gravity, but not something that we deal with in chemistry because gravity is actually the weakest of the 4 fundamental forces that exist in the universe. And you have to have quite a bit of mass before gravity is significant. And we're dealing with very small things in chemistry. There's also what we call the weak force, or the weak nuclear force. And we are going to see the effects of that, but that's not responsible for atomic structure. And so that leaves us with 2 forces. We have electromagnetic force, which deals with charged particles and how they interact. And then we have strong nuclear force, which is how nucleons interact. And nucleons, again, is anything located within the nucleus. And so if we think about this, there's 6 possible interactions, right? We got our 3 subatomic particles, and they can interact with other particles of themselves or the other 2. Now, when it comes to electromagnetic force, right away, right, there is a type of particle that doesn't have a charge, which is our neutrons. And so anytime you're dealing with a neutron interaction, whether it's a neutron to a proton, a neutron to an electron, or a neutron to a neutron, that particular interaction is not going to exhibit any electromagnetic force. However, if you have charges that are the same, such as 2 positively charged protons, they'll interact, and in fact they'll repel. If you have 2 negatively charged electrons, they will also repel. But if you have 1 positive proton and a negative electron of opposite charges, they attract. And so electromagnetic force is going to be the force we work with the most. And keep in mind it always has two possibilities. When you have charged particles or charged molecules, charged ions, there's always an attraction between opposite charges, but there's also this repulsion between opposite charges. And so we'll have to keep that in mind. Now, strong nuclear force only deals with nucleons, and so one of our subatomic particles is not a nucleon. And so anytime you're dealing with electrons, you're not going to have any sort of strong nuclear force interaction. Whoops, put that in the wrong box. And so that leaves, again, three other interactions. You have two protons, a proton and a neutron, or two neutrons. And this is always an attractive force. And so all of the nucleons attract one another. And so if we think about this, this is why we get the structure of an atom we do. We have this tight little cluster of nucleons because of strong nuclear force holding them all together. Now, if we think about it, the protons in that nucleus are also repelling one another because of electromagnetic force. And that's what we'll spend next week talking about, is the idea that not all nuclei are stable. So you have your tight cluster of nucleons in the nucleus, and then you have the electrons surrounding it, right? They are part of an atom because they are attracted to the positively charged protons in the nucleus, but they don't have anything that allows them to attract one another, right? The only force of interaction between electrons is the fact that they repel each other by electromagnetic force. So they spread out and take up this huge amount of space known as the electron cloud. And so it's a really good idea to make sure we understand how those forces lead to our atomic structure. Now, once we talk about our atomic structure, we now want to talk about how we identify a particular particle. And there's two numbers that we're going to use for atoms. We have what's called the atomic number, which is equal to the number of protons. And we'll use the variable z for this. This is also going to be how we determine what element we're dealing with. That's how the periodic table is set up. That's how elements are identified, as the number of protons within a particle. And then we also have our mass number. And the variable we use for mass number is A, and we'll use that quite a bit with nuclear chemistry. This is the number of protons plus the number of neutrons, and it's always a whole number. And one of the things that we want to be careful about is that it is not on the periodic table. There is a number underneath the symbol on the periodic table, but that is not the mass number, because elements exist as what are known as isotopes. And isotopes have a specific mass number that basically is the only way to tell us the number of neutrons in a particular particle. So if we look at our first example here, we have antimony 121. This is the element. 121 is the mass number. And so one of the things to keep in mind is the element tells us what our atomic number is. So if you go to the periodic table and find antimony or antimony, you'll find a box on the periodic table for SB, that's antimony. Comes from the mineral where they mine antimony from, stibnite. And that is going to be the atomic number. And so when we write the isotope symbol, it turns out that the mass number gets put as a superscript to the left of the symbol. The atomic number, if you want to list it, you list it as a subscript to the left of the symbol. It's not really necessary, though, because if you have the element symbol, you now are also implying or telling the number of protons. And so in this case, this has 51 protons. That is what makes it antimony or antimony. By the way, that's my favorite element. Now, as long as you have atoms, an atom is neutral. And what that means is that the number of protons is equal to the number of electrons. And so in an atom of antimony, I have 51 protons, I have 51 electrons. To get neutrons, I'm going to use my relationship for mass number. And so I can take my 121 nucleons, which is my mass number, and subtract my 51 protons, and I can calculate then that I only have 70 neutrons in this particular isotope. Again, that information is basically calculated by knowing the mass number. Or the mass number would be calculated by knowing protons and neutrons. You need two of those three pieces. Let's look at our second example here, cesium-133. So again, you can go to the periodic table and find out that cesium, Cs, is element 55. In this case, we have 133 for the mass number. So again, I've got 55 protons. That's what makes it cesium. As long as it's a neutral atom, I also have 55 electrons. And so to calculate neutrons, I just take my 133 minus my 55. And so this particular atom of cesium has 78 neutrons. Again, there's other cesium isotopes. There's some that are naturally occurring, some that have been made or found in different nuclear facilities and nuclear reactions. What distinguishes an isotope is the number of neutrons. All right, let's talk about the fact, though, that sometimes we get these things that are called ions. These are charged particles. Because not only is the nucleus not always stable because of the competing forces, but it turns out that most atoms are not stable as atoms. Having an equal number of protons and electrons is not the most stable form. And so what we're going to find is that a lot of elements gain or lose electrons to form these things called ions, which are more stable. And so now we have a charge because we have an imbalance between the number of positive and negative particles. And so our charge can be thought of as the number of protons minus the number of electrons. And so keep in mind, if we have extra protons, that means we're going to have a positive charge. If we have extra electrons, we're going to have a negative charge. And so here's an ion symbol. Again, you have the mass number here to the left as a superscript. The charge is put to the right as a superscript. And so the symbol is going to tell you what element you have, and therefore that tells you the atomic number. So you can find Se, selenium, on the periodic table, and selenium is element 34. Again, for neutrons, I can take 82 minus my 34 protons, and I can calculate that I have 48 neutrons. For electrons, what I like to do is I like to think about first the sign of my charge, is it positive or negative? Here it's negative. That means I have extra electrons. The magnitude tells me how many extra. So a negative 2 charge means I have 2 extra electrons. So in this case, I have 36 electrons. And so if you think about it, right, if you take your 34 protons minus your 36 electrons, that better give you your charge, which in this case is 2 minus, and there we go. That checks out. And so you know that you have the right numbers. And so again, our symbol here, 82Se2 minus, represents a particle that has 34 protons, like everything that would be labeled Se. It has 48 neutrons, which tells us that the mass number is 82, right? Because we add that to the 34. And then we have 36 electrons, 2 extra electrons than protons, which means we have an extra -2, or an extra 2 particles that are negatively charged, so an overall charge of -2. Let's look at our last symbol here, iron 58. You go to the periodic table and find Fe. It's element 26. So I've got 26 protons. I have a mass number of 58, so I can take 58 minus my 26 to figure out I got 32 neutrons. And now I have a positive charge. That means I have extra protons. I have 3 extra protons, so in this case I only have 23 electrons. And again, I can check the math. 26 protons minus 23 electrons gives me a 3+ charge. All right, so thanks for your time. Now let's go ahead and look at page 3.